Welcome to this video on displacement, velocity, and acceleration through some examples. So in calculus, once you kind of pass through derivatives, you'll start doing some applications, and one of the neat applications is actually with regards to some velocity and acceleration examples. Now, I'm going to present two examples. The examples are not very easy, but I do hope that they present to you some intuition behind how we can use derivatives to tie in a position in one dimension, so kind of in a straight line, and then tying in into that position, how fast is it moving, so what is its velocity, and then what is the acceleration. So meaning speeding up or slowing down. So the first thing that I'll do is I'll introduce you here. So here's a function. Now, when we are talking about displacement, velocities, accelerations, or position at a particular place, we no longer typically will use f at x, although we could. I could change the s that I've used here for the function. I could have used f, and instead of the t, I could have used x to make it more general, and then students would kind of understand it much better because that's what you use in all your functions. But the reality here is that this s is actually representing a position with respect to some particular line, so some reference point. The t will represent time, okay, so from time starting from 0, which is the initial point, and then as it continues on, so we actually are restricting our time, so we have a domain here where it is between 0 and 16, so that's what we have here. And then we have this funky function in here, basically a polynomial that is telling us where a position, okay, of let's say some particle moving along in a straight line might be. So I would want you to envision this as, you have some straight line. Now it doesn't have to be horizontal, it can be vertical, it can be anything. And then we have, I guess, some reference point. So our reference point, let's say, is some 0. And then we have a particle which is going to be moving along this line. So this particle right here, okay, so I just know at time equal to 0, it's going to be basically just this, 4.6875. So it's going to start somewhere over here, and then it's going to be shifting around, right? And moving, in this somewhere along here. Okay, so left to right possibly might be negative, all right? So it's going to be moving along in here. So that's what I would want you to envision. So it's the position that this S is actually representing, and in particular, that position, you can think back to kind of displacement. Now, I did an introductory video on displacement, velocity, and acceleration. I'll put up a link up above there for you in case you want to see it, but I hope that these examples are going to be self-contained once you understand functions and you understand the derivatives. So if we have this particle, and then this particle is going to be moving along a straight line with respect to some particular reference, so this is a reference 0. So if it's negative, it doesn't obviously mean, okay, that it's at a negative position. It just means it is, to the left of your reference point, and if it's positive, it's to the right of your reference point. That's all that would mean. Now, if we wanted to know what is the speed of this particle, so how quickly is it moving, and then in particular maybe what is its velocity, so velocity means that there's a direction, so is it moving to the right or is it moving to the left? That will be designated with negative if it's moving to the left, a positive if it's moving to the right. If we want to be able to do that, well, once you learn derivatives, then this actually is not a very difficult thing to do, because what you're going to be running into is that you can take the derivative of the position of the particle, and that's going to give you what the actual velocity is. So in this case, if I took the derivative here, it's a very simple polynomial, and I can do that. So this would have been t cubed minus, I guess this is going to be 21 all over 64. I'm not going to simplify things in here, so this is squared, plus, I guess this is 30 over 16t, and then minus, I guess this is going to be 11.25 over 4. So it's still relatively complicated, but that would have been its derivative, or as we would like to write, this is its velocity. Okay, now if we substitute t in here, then we're going to get what the velocity is. So what is the speed? And if we get a positive number, that means that the particle is moving to the right. If we get a negative number, that means that the particle is moving to the left, right? So that's what those positives and negatives actually mean. Those are actual directions. So velocity is a vector. So that would just simply tell us that. Now, once we have this, we can of course visualize this. So I would want to visualize this for you just so that you can understand exactly what's happening, and then I can animate this in some particular way. So here I kind of prepared this right here. So this is how my particle looks like. So on the graph there, so you can see the horizontal is the time, okay, line. So it starts at 0, then it goes, so on. We're restricting it between 0 and 16. And then at the bottom, just below, you have the particle, so the actual position of it, or the displacement. So what is the position with respect to some reference 0? So notice the particle starts off at 4.6, okay, 8, because Desmos rounds this. So that's what we would have in there. And then the line itself, so the orange line that you see, that is just the actual derivative. And on the left-hand side, you can see that at the bottom, I put the derivative as s, and then, I put the little prime because it's the differentiation that we have, and then what the value of it is. Now, you can clearly see that the tangent line at that point is negative, right? It's a slope of a negative. And now, what I'm going to do is, what happens as the time keeps going? So notice that this particular function, we can see that it looks like the particle is going to be going down. And I want you to see there that the particle in red at the bottom is actually moving, right? So it started off right there at around 4.688 and so on. And then it starts to move. So as time keeps ticking, okay, now the particle is getting closer and closer to the reference point, right? And its slope, so its velocity, its speed, right? So it is negative, but here it looks like it's slowing down, right? So it's slowing down. It gets here, it basically is going to flat off at 0. Okay, so that's the slope over here that we would have. And notice on the left-hand side, where it says S prime, okay, at that particular point, notice that it's negative, okay, then eventually gets 0, and then now it's positive. And now the actual particle is going to be moving. Now it's going to be moving, okay, back to the positive side, so to the right. And eventually now again, it's going to be, slowing down, then it kind of peaks, and now it goes, and then it starts to kind of go down, this particle, so it's going to eventually go through the reference point at 0. So that reference point just means, okay, that the particle with respect to what we've defined as 0 on our line is there, and then it goes negative. So its position is negative with respect to the reference, right? So that's what this would be, okay? And then it goes down, and then it comes back again, and then it takes off, as you can see there, and then the actual velocity, okay, notice that it is increasing as we're going through there, okay, all the way down. All right, so you can see that, the tangent line is illustrating for us what the actual velocity is. And you can see that the velocity is changing from positive slopes to negative slopes. So remember, negative just means that the particle is going to be moving in the negative direction. So to the left, in this case, that's how it's been defined. So notice it's moving to the left, moving to the left, moving to the left. Okay, and then eventually here, now it's going to be moving to the right because the slope is positive. So that's what we have in here. So this is a pretty cool animation in here that just shows us at the bottom what the particle is doing. And then we can see that through, as time keeps ticking away, what is happening to that particle. And then the speed we can see through the tangent line, which is attached to the actual graph itself. Now, when you go back in here, so if you wanted to, of course, you can take now and talk about the second derivative. So here we have a first derivative in here, but we can talk about the second derivative. And now the second derivative, so if I take the second derivative of my function, so that would have been now the derivative of the one above, I would get, so this 3 is going to come down, this is going to be 12 over 256. Now it's t squared. So notice it looks like it's going to be now a parabola. This is going to be 42 over 64 t plus 30 over 16. So now this is a parabola that we would have. And this is simply your acceleration. So this is your acceleration, which we can define in this way, or we can define it in this way because it is the derivative, right, of this. Or, of course, we can define it as the double prime of that. So S means the position of the particle. The S prime means what is its velocity, where the signs, positive means moving to the right, okay, negative means moving to the left with respect to your reference. If we had the particle moving kind of up and down, then positive means it was moving up, and negative means it's moving down. So that's just a reference point that we would have. Okay, so that's all that it means, because we can't really have a speed which is negative, right? The negative, the actual sign, just simply means, okay, where's it going? So that means to the right or to the left or up and down. And then if you wanted to find out what is happening to the velocity, how that is changing, you can take the derivative again, and then you will find that as well. So that's pretty neat in terms of trying to see what is happening, okay, with the position, with the actual velocity, and then with the acceleration. Now, the acceleration is interesting because what would an acceleration that's positive mean? And then what is an acceleration which is negative? What does that actually mean? Right? So there has to be some intuition that you should be able to understand. And if I go back in here into our kind of result in terms of Desmos, so if I go back in here on the left all the way at the bottom there, notice I did put double prime, so that really is acceleration. The A, by the way, is not acceleration on the chart. The A is just the actual position. I should have probably put a P in there. That's what I should have done instead of using an A, just so that it's not confusing. But I hope that you'll understand that I'm just serving A, okay, as as I'm moving along in terms of this particular position. So notice in here what happens, and let's try to get intuition. What's happening in here? The position of this particle is moving down, right? So basically it's getting closer to the reference of 0. My velocity is negative, so it is moving to the left. But notice that the velocity, okay, right here, so it's steep, but then it becomes less steep, less steep, less steep. So it looks like it is decelerating, like it's slowing down, right? So this tells me that it's slowing down, and that's the acceleration. And if you notice there, the acceleration within here, so the actual velocity is negative, but the acceleration, notice that it is positive. So the particle is moving to the left, but the acceleration is positive, so it's acting to the right, and that's why it's slowing down this particle, right? Because this particle is trying to move to the left, but the acceleration is in the opposite direction. So if it's going to be moving to the left, but the acceleration is in the opposite direction, it's going to be slowing down this particle, which is exactly what happens. So this particle, notice it's going to slow down, and eventually it's going to flatten out, right? So it's going to stop for an instant, and then because the acceleration, notice, is still positive, so now it starts to push the particle. So if you can envision, this particle is moving to the left, but the acceleration, okay, is pushing it, so it's trying to slow it down within, and it slows it down, eventually it stops. And then the acceleration, because it's positive, it's going to be now moving the particle this way, right? So now it's starting to speed up. So it's starting to speed up right here, but the acceleration, notice it's still positive. Eventually it does turn. Eventually the acceleration turns negative. So now the particle is moving to the right, but the acceleration is no longer this way. The acceleration now, because it's negative, that means the acceleration is to the left. So that acceleration now to the left, because this particle is moving to the right, now it's going to be slowing it down from this direction. And that's exactly what you see. The velocity is now going to get slowed down, and eventually it stops. So that position stops there. And now notice what happens right here, because the acceleration is negative, okay? And now the actual velocity is also negative, so it starts to speed up because they're both in the same direction. The velocity is in this direction and your acceleration is in this direction. So it's pushing it this way. So it's going backwards, so back to the left, and now it's speeding up. And then eventually, okay, so notice what happens in here. So it's still negative, but now, so as your acceleration turns, notice your acceleration turns in here, okay, within. Now, if you look at the bottom left of Desmos, your acceleration is now positive. So now it's starting to, again, slow it down, and then now it starts to speed it up. Notice both of them are positive, and they're continuously positive. So this particle is just going to fly off in here if we kept going, right? So it would have just took off out, okay, into the positive direction. So that's the intuition within. So to summarize for you, because this is sometimes what your teachers might ask you, and as you're working through this, then what you will find is the following: that if your velocity, and this is, you can multiply it by, so if you can multiply it by the acceleration, if these two, are in the same direction, so if this is positive, right? So if either this is positive or this is positive, this means that the particle would be moving to the right. So whatever you defined as positive, or up, if up is positive, so it's moving in this direction and it is speeding up. It is speeding up. Now, if it's moving to the left, so that means this particle is moving to the left in this direction, but it is also speeding up because the acceleration is in the same direction as your speed, right? And of course, negative times negative is going to be positive. So you're going to get this result, that if you multiply these two mean that the particles are speeding up. And it is, in this direction it's to the right, and in this direction it is to the left. They're speeding up. Now, if it happens that you have your velocity and your acceleration, and let's say when you multiply them together, it is less than 0, which basically means, maybe you're moving to the right, but your acceleration is to the left. So in here, you're going to be moving in this direction. However, you're going to be slowing down. The acceleration is working against you, right? So you're slowing down. And now this, if you're going to the left, but your acceleration is now to the right, so you're moving in this direction right there, you're still going to be slowing down because the acceleration is against you. So when these two are opposite each other, you're slowing down, which means you're decelerating. And if they're in the same direction, so if they're both positive, meaning your velocity and your acceleration, then you're speeding up. So this technically means you are accelerating. You can think about your car and driving, right? So that's what actually happens within. So this little chart is kind of neat to be able to understand what is happening. And it's not just left and right. Of course, it could be up or down, or anywhere you define what is positive and what is negative. All right. Now, typically, we do have a frame of reference with respect to the Cartesian plane. So right is positive, left is negative, up is positive, down is negative. And if you stick to that, okay, and you're consistent, you won't be making mistakes. Even if you are studying physics, for example, where it is actually kind of important, to be consistent in your reference points. So this is a pretty neat example that you have. And here the Desmos right here, okay, is a neat way to be able to kind of go through this entire thing and visualize this. I'm going to try, okay, to share the link for this Desmos so that you can load it up. I'll put it up in the show notes. So hopefully Desmos, when you're watching it, is still around, and it will allow you, to play around with this. You can open up the folders to see, how exactly I have done all of this if you wanted to go through that. And, if there's any teachers, you can certainly use this for yourself to be able to show it to your students. Now, here's another example that I have for you. This example is a little bit different. Since we were talking about left and right, I figured, let's take a look at something like this, which might be a common physics problem, but also fair game for calculus. You might not be able to know how to derive this if you had never had physics, but you should be able to work this whole thing out. So what I want to do in here is I want to be able to sketch this whole thing. So instead of using Desmos, we'll go to Desmos as well, but I want to be able to sketch these now. These are not very difficult to do when you're working with positions, then trying to see what the velocity is, then trying to see what the acceleration is, because we can take the derivatives and we can work with this relatively easily. All right, so let me explain this diagram here on the left. So imagine that's me, the stick man standing on, about 50 meters above, okay, my reference of 0. So I'm going to assume that this is 0. This is your ground, okay, whatever this is, okay, so it's some kind of a ground. I have a ball, and I'm going to be throwing this ball upwards. So this ball, basically what it's going to do on the vertical side, if I throw it upwards, it's going to go up, okay, eventually it's going to stop, and then it's going to start coming down, and it's going to, go through here and hit the ground. So this is what this actual problem represents. And moreover, this equation is a very close approximation, assuming that there is no air resistance, for example, okay, of this problem, okay, as a whole, and how to model it. So we're starting here, notice, at 50, okay, notice my initial, okay, I throw it up with 10 meters per second, so this is my 10 meters per second over here. Of course, it depends on time right there, and then this term actually is the gravity, okay, so it's the acceleration due to gravity, which really pulls everything down, right? As you know, if you toss something upwards as hard as you can, it will fly off in the beginning, but then it's slowly going to slow down, stop, and then come down, because gravity's pulling it down. So that's that third term that we have in here. So my first question to you is, how long does it take for the ball to actually hit the ground, right? So if I asked you that, well, that particular question has nothing to do with velocity or acceleration. All it means is you have to now understand what is the reference point. So ground is 0. So really what I'm asking you is, I'm saying, well, what is t when the position is 0, right? At t is equal to 0, it's at 50. It's because that's where I'm standing. So it's, 50 meters above, okay, the actual reference point. So that's what we have. So if I was drawing this out, this is my y-axis in here. Okay, so I'm basically here at 50. That's where I am at. Okay, and then here, time continues on. So this is going to be my time in here. And what happens is, as time ticks on, this is going to be going like this, right? And then it's going to eventually hit the ground. Now, because this is a parabola, this would technically just keep going if I allowed it to. but I'm trying to find the time t when it does hit the ground. So that's what I'm going to do, because, you know, it will not go through the ground, right? The model just only works there. It's going to bounce off probably, right? But we don't have an actual model for that. We just have a model as it kind of, you know, as I throw it up and then it just comes down. And then I want to know, when does it hit the ground? Well, that is not a big deal for us because this is just simply a quadratic, right? So this is going to be that. Now, if you don't remember, of course, you know, the quadratic formula, I'm going to use it because I have 4.9. I don't want to be factoring this out in any way. You know, I certainly can do that, but let me just use the quadratic formula. If you've forgotten about quadratic formula from, I believe, grade 10, maybe I'll put it up above there for you so that you can take a look at it. So here I'm going to, you know, put this up in a regular standard form. Really what this means is negative 4.9, you know, t squared plus 10t plus 50 is equal to 0. This is my a, right? This is my b, you know, this is my c in my quadratic formula. So within my quadratic formula, so that was, you know, negative b plus minus the square root of b squared minus 4ac divided by 2a, right? That's our quadratic formula. You know, if you really want to know where it comes from and so on, you can take a look back at that video that I linked, and it will link it back, or you can search this channel for the quadratic formula proof. So within here, if I substitute this in, I'm going to get negative 10, you know, plus minus. Let me substitute all this in and work it out for you in fast forward fashion. All right, so welcome back. So here it is, just a little bit of work here. So it obviously time can't be negative, right? So this is nothing that we can use, but this one does make sense for us if we're solving it, so it's positive. So that means, you know, that this right here is approximately 4.37 seconds that it actually hits the ground. Now, you can test it out, right? You can substitute that time in and then see if your position is actually going to be at 0. So I'm going to trust myself that that's what it would be. So I have now found the actual time when it hits the ground. The other thing that I would want you to do is I would want you to envision this, okay? So as time keeps going, right? So this is, you know, some time constraints and so on. But I would also want you to know, okay, when, you know, if I want to sketch this, I know that it's a quadratic. I know because this a is negative, it's going to be a parabola which looks down. But what is this, you know, kind of tipping point right here, okay? That tipping point, now that you've studied derivatives, is much easier to find. You can certainly do that. That you can find from finding the velocity function. So the velocity function out of here, so if I take all of this, right here, let me just copy this, I'll bring it down and paste it. So if I take the derivative of this, which is going to be just simply 10 minus 9.8t, well, this right here tells me what the slope is at every single point, right? It's the speed of that ball moving. That is actually what it is, right? The velocity. So initially, we know, okay, that right here, it basically, the velocity is positive, the slope is positive, but it looks like it's decelerating, right? And that makes sense because the gravity is in the opposite direction. The ball is moving up, but the gravity, the acceleration due to gravity is down. So it's going to be slowing this ball down, right? And eventually, it's going to stop. It's going to be flat for an instant of time. So that velocity is 0. So I can now say, okay, well, this is 0, and I can find out what time this happens. Well, this is an easy equation to solve, right? I can just simply shift this over on the other side. Now divide by negative 9.8 on both sides right here, and I'm going to get, I guess it's approximately 1, a little bit bigger than 1. Okay, so let's take a look and see what that exactly is, although we don't have to be that exact. So it's a little bit over, so 102, okay? Let's say it's seconds. We're going to assume that t is in seconds within here. So that's what I have. So that peak right here, so this peak, the time of that is, I'm going to round it. So let's say it's about 1. So this t is in seconds in here. Let's say this was that many seconds. And now I have exactly what my, kind of the peak point of this position is. Now, I can also find out on the y-axis what that is. I can find out what this is because if I know that it's 1.02, I can substitute this back into this equation to find out what was the peak height of this ball, right, as I threw it up. And that's pretty neat. So if I do that, so that's going to be 50, let's say plus, I guess it's going to be 10 times 1.02, and then minus, and this is going to be 4.9 times 1.02, I guess, squared, right? So that's what I'm going to have, and I will know, okay, that was 55.1 meters. So this is 55.1 meters right here. That's the peak. And notice that I can actually sketch this entire thing now, right? So I know when it hits, so I know that now it's going to be falling down as time keeps ticking away, but eventually it hits the ground. And that's exactly what happens, right, in my peak. So let's take a look. I'm going to pull up Desmos, kind of do it side by side within here to see if, if we were sketching it correctly. So here, let me create another Desmos calculator. And so what do we have here? We have right here, so let's say S at t is equal to, and this was 50 plus 10t minus 4.9 t squared, and there you have it. Okay, so this is how it looks like. But of course, we have a restriction in here. So this was between, 0, right, t. Now we know what the time was. So that was approximately, we said, I guess 4.37, notice 3. There we go. That's exactly what it is. Okay, now because we were rounding there, so notice when does it hit right there. So it's going to be about right here, and you can see that. Okay, so it's just above there, so it has to be at 0. So we were indeed, that's what we would see in the parabola, right? So that's what we would have. And the peak, right? So if we're going along here, notice the peak right there, 55.1, right? Give or take, right? So that's what we had when we were substituting it in. So that was the peak. So with now the derivatives, it's so much easier to be able to sketch these things because we know that the actual peaks, velocities are 0 there, right? Or our derivative, okay, is 0. Now, we can also take this graph and sketch how our actual velocity would look like from here just by looking. We don't have to take the derivative as we did in here. We know that it's going to be a line, but we can see, okay, in terms of what is happening. We know that we have a peak, so that means the velocity is 0 there. So it's going to cross through 0 on the velocity graph, okay, if we have in there. And then it was positive, 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 but it's slowing down. And then it starts to be negative, and then it just starts to slope out. And now we can, we can sketch out this particular, let me just kind of go back in here. If I wanted to know what the velocity is, so certainly we can sketch this out. That's not a big deal to do. It's simply a line, but we can do that from the graph as well because now we understand the actual derivatives. And if you wanted to find out what the acceleration is, well, the acceleration for this, of course, is the derivative right there, which is going to be just negative 9.8. And that's meters per second squared, right? Because again, we're taking it with respect to time, the derivative right here. That's my acceleration. So it is literally a flat line. And that makes sense because gravity is actually a constant, right? So the pull from the gravity is that. Okay, so this example, or these two examples, I hope give you some insight into these velocities and accelerations that you probably are going to be running into your calculus classes. All right, I hope you found this useful. We'll see you in a future video. Bye, everybody.